here's your task. I want you to yourself to run that example project where we create the 2D parallel bonded material. And then I want you to compute the tensile strength, the UCS, and the Young's modulus for that material. And just to give you a little, potentially a little help there, go into the course materials and go into BPM lectures and go into fist package. And in there, you should probably only have 2 files. The most important one being this directory called fist package 7.2. And if you go in there, there's going to be example projects. You're going to go in there, and there's going to be right here, material genesis for parallel bonded system. So open that, and you're going to see a material genesis for PFC 2D. So open that project with PFC 2D. All right. Here comes PFC 2D waking up. And you should get what I have on my screen here. This is the top level data file. That's going to create the materials, or the material, one material. Notice the extension is, I call this a driver file. This is like the main high level thing that does everything else. So I call it a .dvr driver file. And then where I have the parameters, material vessel parameters and material property parameters, since those are just parameters, I call those a data file, p2.dat. And then files that just have fish functions and nothing else, I call that .fis. That's the naming convention. Go for it, hit the green button and run it. And you can look at the material vessel view to see what it's doing. Oh my God, it's done already on my system. Well, it didn't crash. It has on line 36, program exit. And we do that because what we can do is call one of those. What we can do is we can call material genesis and test-run project, just to review this. This is very handy. And this will launch PFC. The system clone will, what it does is it launches a new instance of PFC, opens this project, and then there's this ... continuation, and then it calls in this data file. And this is the material genesis data file, right? It's the driver. And so it does program exit. When PFC exits, it goes to the next system clone and continues. Okay. But let's just do these one at a time. So open up the MatGen project again, and let's look at what we got. And so double click on the save state, PFC mat-matv, and open up the view on the left here called PL-mat vessel. If it's a plot view, I put the word PL- at the beginning for plot. And you understand all this stuff now, right? If you look at the plot items, we have the axes plot item, we have the wall plot item, we have the ball group plot item. We also have the clump plot item. If we had generated clumps, you can also do that with this. We could visualize clumps with a clump plot item. Here's the force chains, and there are no forces in this system, the way we build this. This is the contact force chains that are colored with thickness. That's what that one is, contact force magnitude. And then there's this geometry plot item, which has to do with this microstructural plotting I talked about, which allows you to make those fancy plots of material inside this box. And I'm not going to go into and talk about that. You can read about that in the memo. It tells you what to do, how to set things in here so that you can visualize that stuff. Okay. What else is up here? Documents on the left. These are the other plots that are there. For example, number 5, plot GSD, plot grain size distribution. If you open that, this is now showing you the grain size distribution. What this actually is a table, and tables are a built-in thing in PFC that lets you store XY pairs. And then there's a table plot item, which this is, that lets you plot those XY pairs. So there's a fish function that got called at the end of the right after it created things, which went through the system and computed this grain size distribution, right? So, all right, let's shut this down and let's run the direct tension test. So we're going to go into the directory called pen test, and there's a project. So each test has its own project. So let's open up the 2D version of the tension test project by double clicking on it. And so here is the driver that does the tension test. It takes as input tension test parameters, and then it creates these two different save states. And so, and you can see there that what it does, nothing magical. The first thing it does is restore the save file from one level up in the directory structure. That's what the dot dot double backslash means. And then it reads in some of these support functions. These are just files with fish functions that it's going to need. And then it calls in the tensile test parameters data file. And so if we look at that, looks like all the other data files, there it is, tensile test parameters set. And so these are described in that memo, what these are. And what these are here is, this is the thickness of the grains. It's going to select a layer of grains on the top and bottom. And so it basically needs to have a thickness, and it's going to find all the grains with centroids within that thickness layer. And so I'm making the thickness layer be equal to, this is something that exists, which is the average diameter of all of the balls in the model. So I'm basically saying I want you to get a thickness layer of that diameter, which should give us pretty much one set of balls across the top. This is the strain rate that we're going to be loading this at. And this is essentially telling it to run the test until the load has dropped to 80% of the peak, and then stop. There's also in here some histories that are being monitored. One of the sets of those histories right here, these are the total number of cracks, the number of parallel bonds that broke in tension, the number of parallel bonds that broke in shear, and some other things. It says your boundary-based axial strain, etc. Okay, so go back to the driver and let's just run it. So hit the green button. Boom. You can look at this, everything that's going on here in this plot measurement-based stress axial. So this is the axial stress, and this is the axial strain during the test. If I look at the plot TT specimen, there's a specimen. And this is gonna, I think, break. Oh, okay, mine's done. So let's open up that tensile test project and see what we got. So there's gonna be one of these views is the stress strain curve, but there's no save file loaded in. So if you just go to that view of the stress strain curve, there's nothing, because there's no save file. So the save files are over here. And what you're going to have is the top one is the material that we created 2 levels up. The next one is the state of the system at the beginning of the test, after it's all set to go. And then the last one is the system at the end of the test. Notice 18,000 some cycles here. Okay, what's the tensile strength? So this value at the top is 5 times 10 to the 5 pascals. And so if we turn that into megapascals, it's 0.5 megapascals. Okay, so that's there. We just measured that. Let's look at the specimen. That's this other plot view called plot-TT specimen. And here it is. And what we're plotting here are the axes. You see the axes. We're turned on the walls, but the walls all got removed for the direct tensile test. We turned on the balls, and let's just look at ball, let's say text value group. Ball text value group. I'm going to turn off the fractures. Don't turn off the walls. So ball text area group and then color. So we've got, I'm going to change these colors so you can see this. There we go. And unfortunately, you can't see this legend. It's too small to read. I can kind of see it there. Just making this as big as I can. Right? So these are showing what I call the grip grains. These are the guys that have been identified that are going to have their velocities controlled to move up and to move down. And so that's what these, so they've had different group labels put on them, right? So this, you probably can't read this, but the red says TT grip top, and the other one down here is TT grip bottom, and then the yellow is TT grip knot, right? So that's the guys that are having their velocities controlled to do the test, right? And so then the other thing you can look at here, go to the fourth one, it says ball arrow displacement. So I can turn that on. I can turn off the balls just to see. So there's the displacement field, which makes sense, right? It's pulled aparting below, and there's some kind of disturbance right here in that field. And so that's going to be the cracks that have formed. So we go to this fracture group 1. Now it's going to show, I'm going to turn off the displacements. Now it's going to show those cracks. And we can change the color. And it says PB10 fail, which means parallel bond tensile failure. And so now it's showing me the cracks. I can turn back on the balls. And a trick, in order to see these cracks better, is to get rid of the outline of the balls. And then you'll be able to see this better. So if you go to the ball group any, and we go into shape ball, go into shape, and then here you're going to have outline, and turn that to 0. Now it's much easier to see the cracks. Okay, so let's just do one thing. We stop this test at only 80% of the peak. Let's just keep on running the test further. So we'll rerun the test. So we'll go TT params, and it's this line 9, this load factor. Let's go 0.1 instead of 0.8. We'll run the test till the load is dropped further. We would expect in a tensile test that this load will drop very fast. And then we would also expect that that cracking should go all the way across the specimen. So change that parameter in line 9 to 0.1 and rerun the test. And I'm going to keep this plot on the screen while it's running. And just as an aside, of course, you could add the history of the stress strain curve to this same view, and then you could see the stress strain curve on top of this material, this plot here. So there's my stress strain curve, and it's going to go up to about 5E5. So I'm getting ready, and there. Okay, so we change this to 0.1, then we go back to the tensile test driver file, this one. So go ahead and run that. We can watch what's happening. I'm going to look at the force chains, for example. They're all tension. Red is tension. That's what it says here. Red is tension, black is compression. So here we go. and watch the force chains change as this thing fails. I think it's going to fail at about 18,000. There we go. Boom. I'm going to open it up again. There. I can turn off. I can turn off the cracks. Turn on the cracks. Turn off the force chains. These are the typical things you're going to be looking at. Let's look at one more thing. Let's look at the parallel bond state at each contact. And what we're going to expect is that for the parallel bond state will be 3 for all the guys that are still bonded, but it should be either 1 or 2 for some of these other guys, meaning that it broke. Did it break in tension? Did it break in shear? So let's do that. So this is going to be a contact plot item. Let's look at that parallel bond state and see if it's intact and broken. So we're going to go to the contact plot item. So I can go up here, hit that down arrow, and one of the plot items I can choose is contact. So let's do that. We're going to see all these cylinders. So contact, shape, cylinder, numeric value. I want to find PB state. So it's down there, PB state. And let's go named. Now let's look at this here. I'm going to change the color of my cracks to be blue. Okay, so now I'm zooming in. I'm going to change the PB state thickness of those cylinders so they're not as thick. And notice these intact guys are state 3, which means they haven't broken. And let me check something here. Okay. Now, by default, we're only showing the active contacts. If I click all contacts in the contact plot item, now it's going to show all of them. And so, for example, let's change these colors. State 1 means it broke. Let's make that black. Redraw the plot. This. So there's these guys that are black. State 1. These are inactive. So this is the contact that this is the contact that exists between these two disks, but it's not active anymore, but it still exists in the model, and it has a state of 1, which means it broke in tension, right? And therefore, since I'm using that crack tracking package, it's drawing that blue line perpendicular to that contact, right? It's also showing up here. Here's a contact that exists in the model. It's of state 0, means it's not bonded, but it's still a contact, but it's also not active. If I turn on off the active ones, it's not active. But we talked a little bit about that this business about active and inactive. All right. So there we go. I think I've kind of showed the main things. What other plots are in here? Cracking versus BEA. So here's the same axial strain axis, but here's the number of cracks. So basically nothing happened until, all these cracks formed. 30 cracks formed at this point. And the stress strain curve is dropping very rapidly. So we're essentially breaking this into 2 pieces. So then you could look at the cracking. You can see the cracking occurred at 3.2 e to the -4. Here's the stress strain at 3.2 e to the -4, right? You can see that nothing really happened till the end, which seems to make sense. All right. So we managed to run the tensile test and compute the tensile strength. Now let's go and let's run the UCS test. So I'm going to close PFC. Okay. And let's go to the directory called comp test. So go into that directory, shut down PFC, go into the comp test directory, and open up the comp test project, the 2D comp test project. And in this driver, let's go and comment out the program exit so that we don't have to have this annoying business of PFC shutting down on us. So now let's just run this. So go ahead and launch this comp test driver. Watch me. Okay, I want to show something here. I'm going to start it running, and then I'm going to look at the system and watch the system now. I'm going to turn on force chains. Watch the force chains. Boom. I don't know if you caught that, but you could actually see the compressive force going from the top and the bottom as the platens squeeze together. And you could see that happening. It happened really fast though. So here now, you should have the same thing in this view called CT cell, compression test cell. And in the view, it even says, there's a title for the view right there, compression test cell. Now it's being loaded. Let's look at the stress strain curve. That's a plot right here. This is WSD. This means wall stress deviatoric. So it's measured by the fact of the force on the walls. Wall stress deviatoric versus underscore versus what? Wall-based strain axial, WEA. And in that memo, it gives you the naming convention of what these things are. So here's deviator stress. And in this case, there's no confinement. So the deviator stress, which is axial stress minus confinement, is equal to the axial stress. But this is also the same thing we use to do a triaxial test or biaxial test in 2D. So here's the stress strain being measured. It started at 0.1 MPa because I told it that in the parameters, it has to basically apply some small load in the axial direction because we need to make sure that the top and bottom walls are actually in contact with the specimen before we begin our test. So I chose that to be this value, 100 kPa. So that's why it did that at the beginning. You could make that smaller and probably be okay. So, there's some bumps in my case and the stress strain curve. So let's look at the specimen and let's turn off the force chains. And it's actually showing the fractures, and I'm going to turn those guys to red for tension failure. I'm going to make the balls get rid of the outline, and we're starting to get cracking in this specimen. And here's my stress strain curve. Notice how it's trying to fail. It's having an effect on the stress strain curve every time it cracks. I'm going to look at the other view also, the number of cracks versus strain. And you can see the cracking. Oh boy, it's starting to fail. My guy's starting to fail. And so right now it's in the post-peak stage. It's at 80% of the peak, and that's what I told it to stop at that point. Here's the cracking. There was an episode of cracking, a high episode of cracking, but then it stabilized. And now there's another high episode of cracking, and it's not stabilizing, it's failing. That's the stress strain curve. So what's the UCS? Read it off. Megapascal, how much megapascals? Yeah, roughly 2.6 megapascals. We have a 0.5 megapascal tensile strength, and we have a 2.6 megapascal UCS. All right. What else can we look at here? We can look at all these views have been created. So let's look at this. This is measurement-based radial strain. That's the radial strain. So in this case, that's the strain in the Y, how it's bulking out. Notice the radial strain is positive because it's bulking out. It's not squeezing in. And I'm plotting it again versus minus axial strain. So this is the same axis as the other plot. And notice it's linear. It's just bulking out in a linear fashion before there's any cracking. And then it starts cracking a little, and then it starts cracking a lot, and now the radial strain gets really big, right? So the slope of this in the early stages is the Poisson ratio, right? And what you often would want to do, if you want to look at the slope, you can change the x-axis to the minimum and maximum. So instead of going from 0 to this big number, let's make it go from 0 to 0.3 e to the minus 3. So I'm going to change the y-axis. I'm going to say, see right now the minimum and maximum are automatically chosen. So I'm going to make the maximum be 0.3 e to the negative 3, 0.3 e to the negative 3. Boom. So now I'm zooming in, right? I'm looking more. I've changed the axis, right? So now I can, if I want to make this slope plot, I can do it a little better. Nothing more complicated than that. All right. Other views that are in here. Here is the volumetric strain. Negative is compression is volumetric strain. Negative volumetric strain means it's getting smaller. The volume's getting smaller. And so that's going on. And then when it actually fails, of course, the volume gets really, really big. And so it starts going up like that. All right. What else do we have in here? This is actually porosity of the system. And you can see porosity, this is like 0.12 approximately. And it's not a big change, but the porosity is getting smaller as you keep compressing it, right? And then, of course, the porosity gets really big as it starts to fail. Okay. One last thing to point out, we have these, for example, these this is the value of MEV, that means measurement-based volumetric strain. There's another one that's WEV, which is the wall-based volumetric strain. That means the strains were measured with walls, not measured with the measurement circle. In this case, because it's an unconfined test, we don't get any wall-based strain on the right. So the wall-based strain is not relevant. Instead, it's the measurement-based strain that we need to use. If it was a triaxial test, we would be getting that. And I just want to show that measures thing. So there it is in the 2D system. There's just one. There's a measurement circle that's sitting right in the middle. In fact, if I do measure list, there's actually 3 measurement circles. And in this case, because it's a square, they're all the same. But normally, if this was, say, a 2-to-1 aspect ratio thing, there's going to be 3 of them that span along the axis. They're a little bit in from the boundary, and then there's one near the boundary at the top, one near the boundary at the bottom, and one in the middle. And then what we do is we take the value of stress from all of them and we average that. And we do the same thing with the strain. And then that's the value that we return in this fish variable that we're using when we get the stresses and the strains. Okay. There we go. We've done this. Oh, the modulus. How would we get the modulus out of this system? The Young's modulus. So this is the plot. The deviator stress versus axial strain. The slope of this is going to be, well, it's going to be what I called in here, I called that E prime. And you can read about this, but this is basically the Young's modulus measured based on this stress strain curve. And you can read a little bit more if you're interested in a 2D model. When you get a Young's modulus, you have to assume plane stress or plane strain conditions to get this. And depending on which condition you assume, the modulus will be slightly different. It'll only differ by less than like 5% or so. So for most purposes, this is sufficient. Then this doesn't occur in 3D. In 3D, it's just the slope of that. Okay. So there we go. We've walked through this stuff. All right. So let's shut this down. And let's go to the next step, which is what I want to do here. So we've just run the same thing I ran yesterday and walked through, right? That's the same plot. This is the volumetric strain versus axial strain, right? So we'll call this the starting point material.